Stacy just came and asked me a question about one of the homework problems. Specifically, which one was here? Number 8, 2652. If the Earth didn't spin on its axis but still revolved around the sun, would the sun set in the eastern horizon, on the western horizon, or not at all? Now, I want to look at this one before we get started with the lecture, just to, I don't know why I do things in the wrong order, but I do. Just to make sure we're all on the same page. So right now, we have the Earth. Uh-oh. Where did I put the pin? I was sure I brought it in. It must be in my office. Be right back. Here it is. Okay, so as things stand, we have the sun and we have the Earth that goes around the sun as the Earth rotates. Now, I wrote this based on my memory, but I didn't pay a lot of attention. Where does the sun rise? Every morning it rises in what direction? On your side. The east. Listen to Brandon. The sun rises in the east and sets in the west. So, as we go through this, why is the sun rising? I don't think it's because it's a new day. Why do we have the sun rise? Why is it not always in the sky?
It is always in the sky. It's just not always visible.
The Earth is rotating.
The Earth is rotating, so it rotates into view. It rotates so that it's in view and out of view. So the Earth is rotating, and we're rotating. We must be rotating toward the east so that we see it come up in the east and away from the west. And we're also orbiting the same direction we're rotating. So you notice my arrows for the Earth's orbit, the big path is called the orbit, are the same direction as the small one for our rotation. So we have our simple answers. We have sunrise and sunset because the Earth is rotating. How many times do we have a sunrise in a year? Okay, just a shade over 365 sunrises in a year. What does it tell you about our rotations? We actually go around and we face the sun. Let's just say it's an even 365 times. Now let's imagine this with my favorite visual aid. Let us suppose that that's the sun. And so I'm going to start here and I'm facing the sun. And now I'm going to orbit and rotate like the Earth does, but with different rates. So I'm going to start and go around. Okay, how many rotations have I done now? 1. How many times have I faced the sun? No, still just once. I haven't completed my first day, even though I've done one full rotation, because the sun's over there and I'm still pointing this way. I haven't gotten around to point to it yet. And so I keep going around, and here I have one full day. So I've done more than one rotation. And if I keep going around, now I've done 2 complete rotations. I'm obviously not 2 full days yet. Keep going. And now I'm facing, now I have 2 full days. As you go through, what you'll find is with the complete orbit, because we're rotating the same direction that we're spinning, we will actually have one more rotation than we have sunrises. So the Earth actually does 366.2422 rotations in a year. and 365.2422 days in a year. So they're different by one because we're rotating the same direction that we're orbiting. Now we're just going to answer this question with my same visual aid. So I start facing the sun. And I'm going to go around, and I'm not going to rotate. So I'm just going like this, right? At this point, of course, I still have 0 rotations. How many days have I gone through? I start with the sun here, now it's there. How many days have I got through? Half a day. And if I keep going, how many days have I gone through now? 1. Now, so there's going to be 1 day, which means we're going to have sunrises and sunsets. But then we have to pay attention to which side did the sun, let's start with set on, because that's the easiest one to start with here. So when I was rotating like this, and the sun set on my right side. So sun setting on the west would be on the right side. Now, if I'm not rotating, I go like this, what side of me is the sun setting on? I'm at sunset now, what side is it on? It's on my left. So that means that the side that the sun would rise on and set on is reversed. What if, instead of having no rotation, we were like the moon? The moon is tidally locked, so one side always faces us. If we were like that, what would we have?
All day.
All day, no night, no sunrise, no sunset. If we were tidally locked, so we did 1 rotation in the time it takes us to do 1 orbit. So the question was not asking if we're doing 1 rotation in the time for 1 orbit, it's saying if we did no rotations. Okay, everybody understand the question? I went through all of it because I want to make sure you actually understand the question, understand the reasons for the answer. Okay, there is, of course, homework due tonight. That's just one of the 10 questions. It's our last assignment. Yeah. Yay. So let's continue with review. We only got through chapter 5 in class Monday. So chapter 6 is talking about thermodynamics, talking about heat and temperature. What is the difference between heat and temperature? It's an important question you need to know. Heat is a transfer of energy that occurs because you have different temperatures. Temperature is a measurement that's proportional to the average kinetic energy, to the motion of the particles. So they're fundamentally different things, but they relate because heat always naturally flows from hot to cold. We had 4 laws of thermodynamics. The oddly named 0th law, oddly named because initially no one thought that you would ever have to state that if this thing and this thing are the same temperature and this thing are the same temperature, then those two are the same temperature. But it turns out with a better understanding of temperature, that what temperature means, that wasn't an obvious thing. So they just shoved it in as the 0th law because it was really fundamental. The first law, energy can't be created or destroyed. We usually write this as an equation that says the change in internal energy is equal to the heat added minus the work done by the system. So that's just an equation that says we can have a transfer of energy 2 different ways. We can transfer energy through the heat, that is just a spontaneous energy motion from hotter to colder, or through work, that's something applying a force and having motion. Now the work for thermodynamics was pressure times change in volume. So if you change the volume, you're going to have work. And work is going out if the volume expands. Work is going in if the volume shrinks. The second law is the important statement that says heat naturally flows from hotter things to colder things. It also has other statements like natural processes increase the entropy of the universe. Entropy being a measurement, we call it the disorder, although that's a very interesting explanation. Entropy really means how many different ways could you arrange things and have the same situation. So, for instance, if you are playing Monopoly and you roll 7, you can get 6 different ways. So that would be a fairly high entropy. If you roll 3, you can only get 2 different ways, 1 and 2 or 2 and 1. And so that's a low entropy roll. That's what entropy really is. It's a statistical calculation. Okay, I've already talked about knowing that. This one here, temperature change, we had Q is equal to MC delta T. That is, if heat goes into a material, as long as it's not changing phase, that heat going in is going to make the temperature go up. And M is the mass of the object. C is what we call the specific heat. That's giving us the amount of, well, the ratio between change in temperature and heat and mass. And then finally, thermal expansion. Almost everything expands when heated. Give me the singular example we talked about that doesn't expand when you heat it. Water. Water from the 4 degrees Celsius and down through a range in ice, if you cool it, it expands. If you're above 4 degrees Celsius and you heat it, it does expand. It's normal above there. It's opposite below. And that's because when water crystallizes, it does it because of those dipole forces, which comes up in the next section in chemistry. And those dipole forces, in order to get the hydrogen near the oxygen, it forces a geometry that actually spaces things out. So that's why water is anomalous. It's not normal. So we have the normal equation, change in length is equal to the initial length times a coefficient multiplied by the change in temperature. So you might remember the experiments demonstration with heating up the circle heating up the ball so it wouldn't fit through the circle. Also with the bimetallic strip, they had 2 pieces of metal. You heat it up, one expands more than the other and it curls. Chapter 7, the processes for heat. There are 3 processes. Conduction, which is direct contact. If you put things in direct contact, the motion of molecules in one will hit the molecules in the other, and you have a transfer of energy, a heat. Convection is when there's an intermediary. So if you have a hot object and you have a fan blowing on it, the air that hits the hot object will absorb heat from the object. And then if you stand on the other side, that hot air hits you and you will get heat from the air. That's convection. The air was the intermediary. And finally, radiation. That's electromagnetic waves. That's what causes, when we had, most recently when Larissa was up here, she had the lamp that she made it get hotter and hotter, and you saw it glow brighter and brighter. That's radiation. That's the third method for heat, mechanism for heat. Newton's law of cooling simply says that things will cool faster if there's a bigger temperature difference, or heat faster if there's a bigger temperature difference, depending on which side you're looking at. Is that useful? Sure. In every crime drama you watch on TV, when the detective comes and says, "Can you give me an estimated time of death?" The medical examiner has stuck a refrigerator thermometer into the person's liver, I think it's the liver, and reads a temperature. And based on that temperature and the normal body temperature of a human and the temperature of the air around, he calculates how long it's been based on Newton's law of cooling. The greenhouse effect, of course, that's very important. So we can grow our crops in cold climates in the wintertime, or so we can have life on Earth. In very brief, the Earth's greenhouse effect is because the sun gives off radiation primarily in the visible range, because its temperature is around 6,000 kelvins. That the Earth's atmosphere is transparent to visible light, and so the radiation from the sun comes right through and heats up the Earth. It's absorbed by the surface of the Earth, heats us up. course, the Earth is not 6,000 kelvins. The Earth is somewhere around 300 kelvins. And at 300 kelvins, we emit radiation primarily in the infrared range. And the atmosphere is opaque. It doesn't allow infrared radiation out. So energy comes in, radiation comes in from the sun. Radiation from the Earth gets trapped, can't leave easily. And thus you have more heat that can come in that can flow out, causing temperature to go up until you reach an equilibrium. So without the greenhouse effect, what would life on Earth be like? Not, because we'd all be popsicles. We'd all be frozen without the greenhouse effect. It's vital and important to our life on Earth. But if the greenhouse effect gets too carried away, then we become like Venus, where there once again is no life because it's too hot. It cooks things. So we need the greenhouse effect, but we need it to be in the right range. And that's why people talk about, global warming and how man might be contributing to climate change. I've already talked about water's uniqueness here. The last chapter we did on physics, I did put in here, I don't know why this isn't here because I definitely typed in chapters 9, 10, or 11. Therefore, no magnetism, sound, or light on the final exam. That was what the rest of that sentence said when I typed it. I don't know what went wrong. Let's hope that's the only thing that's not correct about my slides. So chapter 8 was the last one in physics. That was where we studied electricity and we learned important rules like we have two types of electric charge that we call positive and negative. And that like charges repel. So positive repels a positive. Opposite charges attract. So the electrostatic force has the equation of force is equal to K Q1 Q2 over R squared. I'm going to rewrite the Q1, where Q is the symbol we use for charge. The units of charge are in coulombs, named after Charles Coulomb, or probably sound more like Carl in the original language. Coulomb, who did the original experimentation to develop how the force relates. So, in physics, force was one of the early things we learned. Force is anything that pushes or pulls. We have the gravitational force that's always attracted. We're all attracted to everything with mass due to gravitational force. With the electric force, you could have a positive or a negative charge, and positive charges are repelled. Opposites, so positive and negative, are attracted. Make sure you can do that. So that's Coulomb's law. Should be able to calculate the force between things. Then we get to chemistry. So in chemistry, we start off by defining atoms. Atoms being, we have the periodic table back there of all the elements. And once again, I'll give you a periodic table on the test so you don't have to turn around and try to read off that table back there. And the nucleus of an atom has protons and neutrons. And then it has electrons that are going around. You should know a little about the models of the atom. For instance, that the electrons aren't doing circles around the nucleus. We don't know what they are doing. All we can calculate is where they're likely to be found. So we say there's a cloud of electrons. But the electrons have different energy levels. And so when we had the gas out here, which once again, Larissa had out on Friday of last week, we saw specific colors instead of a continuous range of colors because the electrons can only have specific energy levels, and the light that was given off was due to electrons falling from a higher energy level to a lower energy level. So there are only specific gaps available, and we were seeing light with energy HF, so only certain frequencies available. When we put the electrons in, we have shells. The shells, we call them energy shells because the lowest energy shell, the 1s, can only have 2 electrons in it. And then you go to a higher energy shell, the 2, and you have the 2s and the 2p. So we put 2 electrons in the 2s. So if you look back at the periodic table, the top row is just the first shell has H has an electron in 1s. Helium has 2 electrons in 1s. You go to the second row, lithium has, in addition to that, 1 electron in 2s. Beryllium has 2 electrons in 2s. Then you have to jump across to boron, which has the 2 electrons in 1s, 2 electrons in 2s, and 1 electron in 2p. And it keeps filling. So the second row is filling up the second energy shell. The third row you would expect would be filling the third energy shell, right? Wouldn't that make perfect sense? And everything that is on the third row is filling the third energy shell, just the same way the second row is filling the second. Except for the third energy shell has 10 additional electrons in that shell that we don't see on the third row. Those 10 additional electrons are filled on the fourth row. That's what the gap there was between beryllium and boron, magnesium and aluminum. That was a place for putting in the 10 additional electrons. So going from scandium to zinc, you're actually putting electrons in the 3D. So it's going to the third shell even though you're on the fourth row. So the periodic table is depicting the energy levels of the electrons as well as just simply showing how many protons are in the nucleus. So you can just count 1, 2, 3, 4, 5, 6, 7, 8, and so on. Each element's just going up by 1. So what is the atomic number? It's the number of protons. It's Z, and it's the number of protons. What about the atomic mass then? You can use what Brandon said as your springboard. It's protons plus neutrons. So that has the number A, or letter A, and it's the number of protons plus neutrons. And so we usually don't use those two numbers to describe a nucleus. You should know the word isotope. Isotopes are elements that have, well, you can have like 2 isotopes of iron. They have the same number of protons but different number of neutrons. So isotopes, that P, protons, they have iso and then P for protons. Okay, it's topes, isotope, and then P for protons. Isotones is a word you don't have to know, but isotones is the same number of neutrons and different number of protons. So iso to N for isotones. Take this one to heart. You don't have to memorize the table. I'm going to give you that table, okay? Right? It would be a waste of your time to memorize it. But you need to understand what it means, which is why I've spent our time here, the first chapter for chemistry, talking about what it means. And you should be able to identify these columns. The alkali metals is the first column. That's a Roman numeral 1. The alkali earth metals, that's a Roman numeral 2. That's not 11. And then we have the halogens, and that's not Roman numerals now, that's Roman characters, or Roman. Somehow I'm thinking maybe I should say that it's Arabic. Yes, Arabic. It's Arabic numbering there, 17, 18, for the halogens and the noble gases, the last 2 columns. The halogens are 1 electron short of completing a shell. They really want additional electrons. We say that means they have a high electronegativity. The alkali metals have just 1 electron in the their highest shell, they're kind of happy to give up that one electron. And so the difference in these are happy to give up electrons, whereas the halogens, they want electrons. Hence, we can make nice salt, strong ionic bonds between halogens and alkali metals. The noble gases, what makes them noble? I didn't hear what you said, I'm sorry. But they have a completed shell is the right answer. They have a completed shell. They are just happy the way they are. They don't want another electron. They don't want to give up an electron. They just want the status quo. So they don't mess around with other atoms. That's why they're considered noble elements. The transition metals are the things in there, those 10 columns in the center that are offset in their filling from the shell. Those are very similar because their chemical behavior is more defined by the for these, the S than it is for those d orbitals. Finally, for chapter 12, quantum theory. What does it mean if something is quantized? It can only have specific values. So, for instance, you can have 1 penny or 2 pennies or 3 pennies, but you can't have somewhere in between. You can't have 1.6 pennies. So it's quantized. You can only have integer multiples of the pennies. Doesn't always have to be integer multiples, but it has to be only certain values. So when we talked about the electrons having different energy shells, we had quantized energy levels, only specific energies that the electrons can have, not just any old value. And so the distinct line spectra are caused by, you can only have energies like this, and so those spectra are caused by electrons dropping from a higher energy to a lower energy, and there's only certain energy changes that electrons can have. And since, as we learned at a later date, light has energy is equal to HF, then there's only certain frequencies because we have only certain energy levels. Chapter 13. Chapter 13 was radioactivity, which we had actually talked a little bit about in the physics section because we have a lot of overlap between our sciences. That's why we have a physical science class where we can see these overlaps. So radioactivity has to do with the nucleus of the atoms. Does not have to do with the electrons orbiting it. Has to do with the nucleus. And radioactivity is where the nucleus is not perfectly stable. It's kind of stable. I'm going to use this because this will be very easy to deal with. I put it on here, and it's stable, right? It's balanced. But just a little disturbance, and it falls to a lower energy state. That's what's going on with something radioactive. And when this fell to the lower energy state, you could hear a sound emitted because it fell to the lower energy state. With atoms, when they fall to lower energy states, they're going to give off energy in a couple different forms. And you only have to know these 3 forms: alpha, beta, and gamma. Alphas are helium nuclides, 2 protons and 2 neutrons that come flying out of the nucleus. So it just cut off a piece and threw it out. Alpha particles, because they have a fairly high mass, 2 protons, 2 neutrons, that's high compared to the mass of things like electrons, they're easy to stop. So remember you had the question that I ended up, removing one from the number of points on the test because of it. That's asked, what's the minimum protection you need from alpha particles? What was the answer?
Um,
Yeah, just sunscreen. Those alpha particles will be completely, your body's completely protected. They're going to be absorbed into sunscreen before they get to your skin. If you don't have sunscreen, well, they're going to be absorbed by your skin. So the only real danger from the alpha particles, as long as they're outside your body, is skin cancer. You absorb those alpha particles, that's a lot of energy. It's the energy that's the problem. That energy can break bonds in your body, bonds in your DNA, and those bonds could potentially reform incorrectly, creating a mutation. If that mutation is viable, that's what we call cancer. And so that's where the concern is, but as long as the alphas are outside your body, not a big concern. If they're inside your body, now it's a much bigger concern because it's going to be absorbed by something important inside your body. And so that's the reason why you never, ever, ever, ever have food around radioactive materials, because you don't want to ingest something that's going to be radioactive, because then it's going to be absorbed by you and your danger goes way up. Beta is an electron. There is also the beta plus, which is a positron. It's an anti-electron. That's an electron coming from the nucleus, which has 0 electrons in it. Question is, how do you have an electron come from a region that has no electrons? It's actually created in particle interaction. You're going to have something like an up particle decays into a down particle and a W minus. Did I do that right? No, the other way around. Down particle will decay into a proton and W minus. And then that W minus will decay into an electron and an electron antineutrino. So it was created, it didn't exist beforehand. So those electrons are pretty hard to stop. So you want to have shielding. The last one, gammas, that's electromagnetic radiation. Electromagnetic radiation goes through lots of things. You go to the dentist and they take an X-ray. X-rays are also electromagnetic radiation. They go right through most of your tissue. But the more dense tissue will stop it, and so that's why they do it. They take a picture and you have the X-rays go through a bunch of tissue, but it's absorbed by others and they can see the shadow. Radiation dose and where we get it from. We had a lab where you went through and calculated how much dose you receive annually and where it comes from. And one of the things that was very interesting was about 20% of the radiation dose we get comes from radon gas. Where does that come from? The Earth has a bunch of uranium in it. And that uranium decays, giving off alpha particles along the way. Alpha particles, helium nuclei. That's what creates the helium that we have in the air. When you have a helium balloon, that was originally alpha particles that came from the decay of uranium or one of the atoms between uranium and lead in that decay sequence. And so radon gas is the only gas in all of the elements in the decay sequence for uranium. And because it's a gas, it's much more mobile. And so we worry about that radon gas because it's mobile, whereas all the rest of the decay products are solid, they're not mobile. Question?
Sorry, just backtracking a little bit. So is it harmful when people put helium in their bodies?
No. No, I had a teacher in grade school who said that it shrinks your vocal cords. And if you took too much, you would be permanently stop talking that squeaky voice. And she was just dead wrong. There are a couple verified cases of people dying from helium balloons, but in all cases, there are people doing stupid things. Like one of them is a huge balloon and the guy pulls it down around his waist. Ha ha ha, look everybody. What does he not have? Oxygen. And so there are a couple cases like that. There was one that made the news big time somewhere around 5 years ago, where a family claimed that the daughter just inhaled helium from a balloon and died, but it turned out there was a lot more involved than that. Okay, so radon gas, because it's a gas, it's a concern. That gas moves out of the ground and then it decays, and if it you have the radon gas decays, and then if it attaches to a chunk of dust and you breathe it in, the stuff that comes next after the radon gas, if you breathe it in, will damage your lungs. And thus, radon is I think it's the second leading factor for lung cancer. Now, cigarette smoke is somewhere like 80%, or maybe it's in the 90s. It's a huge factor for cigarette smoke. Radon gas is the next one, but it's a much, much smaller risk than cigarette smoke. We talked about half-lives being the time for 1/2 of our material to decay. So if something is 3 half-lives old, it'll have had half decay in the first half-life, half of that decay in the second half-life, half of that in the third half-life. And so it'd be 1/2 times 1/2 times 1/2, or 1/8 remaining after 3 half-lives. And it's that fact that we use for radiometric dating. If you can determine how much you started with and how much you have now, assuming that it's a constant half-life, that it doesn't change over time, you can determine the age of something. So there are 3 things you need. You need to know how much you started with. Nobody was here at the start time to verify that usually. You need to know how much you end with. Well, that we can make direct measurements for. And you need to have a constant half-life. We can measure the half-life now. It's an assumption that it's always been the same. We consider it a very strong assumption, but it's still an assumption. Nuclear fission and fusion. You can remember we had that energy graph. I'm not sure if yours went up or down. It went down. You had a homework problem that asked you about taking uranium and breaking it into 2 equal pieces, or 3 equal pieces, or something like 92 or something equal pieces, or 235 equal, I don't remember what the number was. And the key is this graph was showing binding energy per nucleon. The nucleus is held together, and whatever holds it together we call the binding energy. That binding energy is this strong, weak nuclear force is holding it together. But we have that binding energy, the lower it is on this graph, the more tightly the nucleus is bound. And with Einstein's equation that says E equals mc squared, if it is more tightly bound, you had to release energy to get there. It's like dropping something to the bottom of the well. You started with potential energy, it fell to the bottom, had kinetic energy, hits the bottom, it makes a sound, that's the energy, going out. And so if you move from a higher point to a lower point in that graph, it's going to release energy. And so you would release energy going to, cutting into 2 equal parts. You'd release even more going to cutting to 3 equal parts because it's lower on the graph. But if you cut it into like 92 equal parts, it's really high on the graph and it won't release energy at all. You would have to put energy in to make that happen. And so in our stars right now, the sun is fusing hydrogen to helium. And so it's going from up here at 0 for hydrogen down, something like this for helium. And because it's going down, it's releasing energy. And when the sun is dying, it will go on down and produce, going down as far as about carbon or oxygen. And then our sun will be done. And so we're going to have a carbon oxygen, we call it a white dwarf, remaining when the sun dies. If you have a supermassive star, it can go all the way down to the bottom. Do you remember what elements are at the bottom? No?
Iron.
Yes, iron. Fe. Iron's at the bottom there. So a massive star will fuse larger and larger things. So if you look at Betelgeuse is a red giant. It was in the picture that Larissa had for us. It's a red giant. What does it mean if it's red?
It's cooler.
It's one of the cooler stars. Giant, it's really large. because it's really large, what does that mean about the luminosity, the light it gives off? Okay, the larger it is, the more light it gives off. What about being cool? What does that tell you about the light it gives off? The lower the temperature, the lower the light given off. So you have two competing things, but obviously Betelgeuse is very bright because it's really, really, really large. It's really large because right now, actually, Betelgeuse is almost certainly dead at this point. But it takes time for light to travel to us, so we haven't seen its death yet. And so at the stage we're seeing, Betelgeuse is not fusing hydrogen to helium anymore. It's now fusing things like, carbon, oxygen, nitrogen. We call it the CNO cycle. Carbon, nitrogen, oxygen is the order. It's probably doing something like that right now instead of fusing hydrogen to helium. Why? Because it used up all the hydrogen it had. Gravity, always attractive, started crushing it down, making the temperature in the core even hotter so they could fuse these other things. And eventually Betelgeuse will fuse until its core is basically iron. And then you're at the bottom. You can't do any more fusion to release energy. And then gravity's going to take over. It's going to collapse. And when it collapses, you're going to have a big crunch at the core. And that crunch at the core is going to put in energy and make things zoom back up that way. And so it's going to create smaller elements during the death stage, which is really interesting. So that it might end up with a core that's exclusively neutrons. We call it a neutron star. So a neutron star is like the nucleus of an atom, but only neutrons with no protons. Really bizarre. Or it could have so much mass that gravity can crush the neutrons and it becomes a black hole. So fusion is the key to what's going on in our stars. Now for the bombs, North Korea is threatening to, fire a nuclear missile at the United States. That nuclear missile could be a fission bomb or a fusion bomb. In warfare, there have only been 2 nuclear devices ever used. Those are both fission bombs. That is, they started at the high end, split into smaller pieces, giving off energy. Fusion bombs are created by, you have to create really high temperatures and pressures to make fusion occur. And so they make a fission bomb, and inside that they put hydrogen. So they'll create high enough temperatures and pressures for the hydrogen to be forced into fusion. And that's how they make a fusion bomb. And so if North Korea was going to try to bomb us with a nuclear bomb, if they have a fission bomb, they probably have a fusion bomb, and that's going to be much more lethal. So they're more likely to use that. Of course, there's also a lot of saber rattling that goes on in politics. You guys probably are too young to remember Saddam Hussein always, threatening the U.S. and stuff. And then if the U.S. retaliates, he backs off. And why are you picking on me? And so there's a lot of posturing, but that's not part of our review. Question? Okay, chapter 14. This is where we talked about making chemicals. So we have things like, all of these words are vocab words that you should know. A chemical is not, by definition, a bad thing. It is just an element or a combination of elements. A molecule, molecule and chemical, at least in my mind, they're identical in meaning. Molecule is where you take 2 elements and put them together. But we have monatomic things like helium gas, which I've always considered a molecule. Probably technically it's not because it doesn't have any bonds. Question, Brandon.
Oh, sorry. So chemical can be one thing, but molecule has to be...
I believe molecules have to be 2 or more.
Okay. But it can be like 2 of the same element?
Yeah.
Okay.
We have elements, which are each one back there, each different type of atom is a different element. So hydrogen is one element, helium is one element. And if you have helium-2, the example that Brandon was, in the ballpark what Brandon was saying, helium-2 is a molecule, but it's still elemental because there's only one type of element. A compound is going to have more than one type of element. So water is a compound because it has both hydrogen and oxygen, H2O. And then we have mixtures. That's mixtures of different kinds of molecules. You had homogeneous mixtures and heterogeneous mixtures. Homogeneous, you look at it and you can't tell it's a mixture. Heterogeneous, you can look and see. So we had the example of a pepperoni pizza as a heterogeneous mixture. True story. I was raised a vegetarian. My dad was a vegetarian. We went on a trip and we were ordering pizza, and these guys said, "Hey, why don't we get a pepperoni pizza?" My dad's sure. Is that kosher? Sure it is. So we got it because Dad didn't know pepperoni was meat, much less unclean meat. Okay, alloys. Alloys are mixtures of metals. Metals have a unique bond. They're not covalent bonds. They're not ionic bonds. They are bonds where electrons are actually dissociated from the nuclei and just running through the material. And those electrons hold the nuclei together. So it's what we would call a matrix force. But because it's not a bond between atoms in a metal, you can easily replace one atom with another type of atom that will do the same kind of donating electrons. And so that's what alloys are. And so a lot of the metals we use, things like stainless steel, is an alloy. Iron is the primary component of stainless steel, but then you have a certain amount of carbon and a few other things that are put in there to give it different chemical properties. And so what's a physical property compared to a chemical property, right? We had a lab where you had to try to define that, and that was kind of tough. But the definition is not tough. What's the definition of a physical property versus a chemical property? You're giving an example of a physical property change. The what? Rust? That's actually a chemical change. A chemical change is where the molecules change, and rust is an oxidation. You have iron that forms bonds with oxygen. So that's a chemical change. I want physical, yeah. Okay, water to ice. It changed its physical form, but it did not change the molecules. That's a physical change. Same molecules, just looks and behaves different. Chemical change is where you change the molecules themselves. Oh, and be able to name the simple compounds. Remember our rules like a sodium and a chlorine? You take the ene off of the chlorine and replace it with ide, and it's sodium chloride. And if you had the option of having one or two, then you use prefixes. So HO would be, if you want to be really technical, monohydrogen monoxide. And H2O would be dihydrogen monoxide. And H2O2 would be dihydrogen dioxygen. But what do we usually call them? We have common names. Water, hydrogen peroxide, okay, now I've got to think about the difference in hydronium and hydroxide. It's hydroxide, and hydronium is H3O. So, the special names, you don't have to know all those because there's too many of them. But make sure you have the simple naming convention. Okay, then we had how atoms bond. So we had that Lewis dot structure, which Jocelyn invented for us, right?
Oh, yeah.
What's the purpose of the Lewis dot structure? Yeah, to show the valence electrons that can be used in our bonding. And so we can use the dot structure to understand how bonds are going to be made because we need to have the right number of electrons in our compound, and each atom should have 8 valence electrons with the exception of hydrogen. We had ionic bonds. Bonds formed between two things with very different electronegativities. Covalent bonds formed between things with very similar electronegativities. And then we had the special ones. The ion dipole, that is, you have something like water that has a positive and negative side. If you have a positive ion, it's going to be attracted to the negative side of the dipole of the water. Dipole, that's what happens with our water bonds. It's called a hydrogen bond because it's so common. You have the dipole of the water and another water, and the O of one water forms a very weak bond with the H of another. These are shown in order generally of strength. Now, these two up here are the strongest. And actually, your very strongest is going to be covalent, like diamond is a covalent bond. But then you're getting weaker as you go down through these. Dipole-induced dipole is you have something that has a uniform charge distribution, but a dipole comes by and the positive side pushes positive away and attracts negative, and now it forms an induced dipole, and then they bond. Induced dipole is two things that are uniform come together and force each one to form a dipole. Very, very weak. Okay, that's where we shall end for today, and we'll continue our review again on Friday.